The images arrived without warning. Deep-field exposures from the James Webb Space Telescope, staring into a patch of sky no bigger than a grain of sand held at arm's length. And in that patch, galaxies. Not smudges, not embryos, galaxies. Structured, massive, mature, at a distance the standard model insisted should show nothing but hot primordial gas. The press releases called them surprising. The papers called them in tension with predictions. The astronomers involved chose their words carefully. But the deeper meaning is harder to soften. A universe that is 13.8 billion years old should not contain what Webb is seeing. Either the timeline is wrong, or the physics behind the timeline is wrong. There is no third option that leaves the textbook intact. And that is where this story actually begins. You have heard the number your entire life, 13.8 billion years. It appears in documentaries, in classrooms, in every casual explanation of where everything came from. It sounds precise. It sounds settled. It sounds like something scientists measured the way you might measure a room with a tape. It is not that. The universe's age is not observed. It is calculated. It is the output of a specific model called lambda CDM, fed a specific measurement from a specific satellite, producing a specific number that depends on every assumption inside the model being correct. And right now, those assumptions are under a kind of pressure they have never faced before. Two different, rigorous methods of measuring how fast the universe is expanding are giving two different answers, and the gap between them has grown, not shrunk. In 2023, a peer-reviewed paper in a serious astrophysics journal proposed that the universe may actually be closer to 26.7 billion years old, nearly double. Wherever you are watching this from, whatever hour it is on your side of the planet, ask yourself what you were taught. Because the number in your head may already be obsolete. By the end of this, you will understand why every textbook diagram of cosmic history is starting to look less like a fact and more like a draft. You will see how a measurement most people trust completely has been quietly fracturing for a decade. And the most uncomfortable part is not that the number changed. It is what had to change to make the new data fit. The public version of the story is clean. In 2013, the Planck satellite finished mapping the cosmic microwave background. The faint afterglow of the Big Bang spread evenly across the sky in every direction. That map was the most detailed baby picture of the universe ever taken. Scientists fed it into the lambda CDM model, the standard framework of modern cosmology, and out came a number. 13.787 billion years, plus or minus 20 million. Precise to 4 decimal places. Textbook material within months. A number so specific it seemed to end the conversation. That is the version most people know. That is the version most people trust. Now watch what happens when you look at it carefully. The Planck measurement gives one value for the Hubble constant, the number that describes how fast the universe is expanding. Roughly 67.4 kilometers per second per megaparsec. But when a completely different team, called JWST, measures the expansion using nearby stars and supernovae, they get a different number, roughly 73.0. The disagreement is now above 5 sigma, which in statistical language means the odds of it being coincidence are effectively 0. Think about what that means. Two of the most careful measurements in the history of science, using different techniques, checked and rechecked for years, refuse to agree. And the gap is not closing, it is hardening. That is only the first crack. The model that produces the 13.8 billion figure also requires that 95% of the universe be made of things we have never directly detected. Dark matter, dark energy, two invisible ingredients invented to make the equations balance. They may be real, but no one has isolated them in a laboratory. No one has held one in a detector. And then there is the third problem. The model assumed early galaxy formation would be slow, cautious, gradual. Webb has now shown that it was not. The confidence in 13.8 billion was never really about the number. It was about the model that produced it, and that confidence is leaking. So how do you measure the age of something no one was there to witness? The answer reveals the first fragile assumption. There are three main ways to age a universe, and none of them is what you would call direct. The first is the cosmic microwave background. You measure the oldest light in the sky, the radiation left over from when the universe first became transparent, and you work backward using the current expansion rate. The math tells you how long ago that light was released. The second is the cosmic distance ladder. You start with nearby stars whose distances can be measured with parallax. Then you use those to calibrate Cepheid variables, stars that pulse at a known rhythm. Then you use Cepheids to calibrate Type 1a supernovae, exploding stars bright enough to be seen across billions of light years. Each rung of the ladder depends on the rung below it being correct. The third is stellar aging. You find the oldest stars you can identify, measure their composition, and use that to set a floor. Whatever number you get, the universe cannot be younger than its oldest stars. That sounds obvious, but as you will see in a moment, even that flaw has caused problems. 3 methods, 3 witnesses. 3 blurry accounts of the same crime scene, and a growing suspicion that none of them is telling the full truth on its own. And here is the part that should bother you. Every one of these methods assumes the expansion rate of the universe has behaved a specific way over time. If that assumption is slightly off, the age does not shift by a few million years. It shifts by billions. The history should humble anyone who thinks the current number is safe. Before Edwin Hubble's work in 1929, the universe was believed to be static and eternal. Before the 1990s, the accepted age was around 20 billion years. Every previous generation of astronomers called their number settled. Every one of them was later revised. Measuring the universe is not like reading a ruler. It is like triangulating a suspect from witnesses who cannot quite agree on what they saw. And the rungs of the ladder are now showing something no one wanted to see. The Hubble tension is the name astronomers give to the disagreement, and it has become the most important unsolved problem in cosmology. Not because it is dramatic, because it refuses to die. For years, physicists assumed better instruments would close the gap. They didn't. For years, they assumed better calibration of the distance ladder would fix it. It didn't. When Webb turned its mirror on the Cepheid variables that anchor the shoe's measurement in 2023 and 2024, everyone expected the ladder to wobble. This was supposed to be the moment the discrepancy resolved. A cleaner measurement, better resolution, fewer stars blurring together in old Hubble images. Instead, Webb confirmed the ladder. The Cepheid distances held, the tensions survived. Then, a third independent method entered the picture. The tip of the red giant branch, a technique using dying stars in nearby galaxies as standard candles. It produced a value somewhere between Planck and Shoes, but still incompatible with a single answer. 3 methods, 3 refusals to reconcile. This is where the story stops being a data problem and starts being a physics problem. Because here is what physicists actually hope for when they see a disagreement. They hope the error bars are large. Large error bars mean the true answer might still fall in the overlap. But the error bars in this case have been shrinking for a decade. The measurements are getting more precise, not less. And more precision without convergence is the worst possible outcome. It means the disagreement is not noise, it is signal. Something inside lambda CDM is wrong. Now, to be fair, this is not a scandal. This is not a cover-up. This is what an active, honest science looks like when it collides with the edge of its own model. Scientists have not hidden the tension. They have written hundreds of papers about it. Entire conferences have been organized around it. Proposals for new physics have multiplied. But the public framing has been slower to admit that the edge is here, right now, in front of us. What the community writes to itself and what filters out to the public are two different documents. And then Webb started sending back images of galaxies that should not exist. Consider a galaxy called JWST Z14-0. Webb confirmed it in 2024. It sits at a redshift of about 14.32, which means the light reaching Webb's mirror left that galaxy roughly 290 million years after the Big Bang. In cosmic terms, that is a newborn universe, not even old enough to walk. And yet the galaxy is there, structured, luminous, producing stars at a rate the model does not know how to account for. It is not alone. Webb has found a growing catalogue of massive, mature-looking galaxies at redshifts above 10, packed into an era that the standard framework predicted would still be dark, thin, and mostly featureless. Then there are the little red dots. Compact, unexpectedly bright objects appearing throughout the early universe in numbers no simulation predicted. Astronomers are still arguing about what they are. Baby quasars fed by supermassive black holes that grew too fast. Overdense starbursts, something entirely new. What they agree on is that there are far too many of them for the timeline anyone was working with. Every simulation of the early universe run before Webb launched has now been contradicted by what Webb actually saw. The intuitive response is to say, fine, star formation started earlier than we thought. Push the ignition switch back 100 million years, adjust the model. But the math does not bend that way. To assemble a galaxy of that mass at that redshift, you need either more ordinary matter than the early universe had available, or a longer runway of time than the model permits. There is no third variable to tune. One of those two things has to give. In 2016, Hubble spotted a galaxy called GN-Z11 that already stretched the model to its limit. Astronomers called it an outlier. Webb has now found dozens like it. Outliers become a pattern. Patterns become a refutation. And now the harder question begins to form. If the timeline is wrong at the beginning, what does that do to the number at the end? Try to feel this the way your body might, not the way a textbook wants you to. Every atom in your body heavier than helium was forged inside a star. The iron in your blood, the calcium in your bones, the oxygen in every breath you have ever taken. All of it was manufactured in the pressure of stellar cores, scattered by stellar deaths, and reassembled billions of years later into the specific arrangement of matter you happen to be. That process needed time. Generations of stars, each one enriching the gas of the next. If Webb is right, and stars started forming earlier and faster than the model allows, then the machinery that built human biology started running earlier than anyone thought. You are older, in a sense, than your family tree suggests. Not you personally, the material you are made of. The atoms in your hand may have been forged in a stellar generation the standard timeline does not know how to account for. The night sky is a time machine. You already know this, but let it land properly for a second. Every point of light you have ever seen is a message from the past. If the timeline of the universe shifts, so does the age of every message.
The Andromeda light hitting your eyes tonight is 2.5 million years old.
That number is safe, but the redshift of a distant quasar depends on a model. Change the model, and every distance in the far universe retimes. This chapter is not about doom. Nothing is ending, nothing is falling out of the sky. What is ending is a specific kind of confidence. The version of reality most people carry around, the tidy chart with 13.8 billion years at one end and today at the other, has softer edges than the confidence in your schoolbooks suggested. And if the timeline is elastic, so is the theory of what stretched it in the first place. The stretch itself may be older, stranger, and less understood than any textbook has admitted. Here is a fact most people never absorb properly. The model that gives us 13.8 billion years requires the universe to be composed almost entirely of things no one has ever seen. About 68% dark energy, about 27% dark matter, roughly 5% everything else. Stars, planets, gas, dust, you. Every atom of matter you have ever touched, or eaten, or been, adds up to a small minority of what the universe is supposedly made of. Dark energy was invented in 1998 to explain why the expansion of the universe is accelerating instead of slowing down. It has no known particle, no laboratory signature, no independent confirmation outside cosmological observation. It exists in the equations because without it, the equations do not match the sky. Dark matter has been searched for underground for decades by experiments with names like Lux, Xenon, and Panda X. Detectors buried under mountains to shield out cosmic rays, waiting for a single interaction. The interactions have not come. Billions of dollars, thousands of scientist hours, and the most sensitive instruments ever built have all returned the same answer. Nothing. Whatever dark matter is, it either does not interact the way theorists predicted, or it is not the kind of particle they have been looking for. Then in 2024, results from the Dark Energy Spectroscopic Instrument suggested that dark energy may not even be constant. It may be changing over time. That is a small sentence with a large consequence, because the standard model does not permit it to change. If DESI is right, the anchor of the entire framework is loose. The historical parallel is uncomfortable. Ptolemy's Earth-centered universe also worked mathematically, as long as you kept adding epicycles. Circles inside circles, invented every time an observation refused to fit. The model was accurate. It was also completely wrong about what was happening. Dark matter and dark energy may be the deep structure of reality, or they may be modern epicycles. Nobody yet knows. And this is exactly the tension the public was never told about. Read the language carefully, not the headlines, the actual papers. When Webb's early galaxy results came out, the phrase you saw again and again was "in tension with predictions." That is a scientifically responsible way to say something specific. Translated into plain English, it means the model is wrong, or the observations are wrong, and the observations keep replicating. But in tension sounds gentler. It sounds like a disagreement that will resolve. It sounds like the model still has authority. The softening is everywhere once you learn to see it. Press releases prefer surprising over model breaking. Grant funding rewards researchers who work within existing frameworks rather than against them. Textbooks lag primary literature by 10 to 20 years, which means the version of cosmology taught in most classrooms is a version physicists themselves would flag as outdated. And public trust in science is treated as a resource so fragile that uncertainty must be filtered out before it reaches the public, even when uncertainty is the honest state of things. In 2023, Rajendra Gupta published a paper in the monthly notices of the Royal Astronomical Society, proposing that the universe may be closer to 26.7 billion years old. A serious journal, a serious argument. His model, drawing on ideas about tired light and evolving physical constants, attempted to explain the JWST early galaxy observations without breaking the rest of cosmology. The response in mainstream coverage was cautious to the point of dismissive. Interesting idea, most outlets said, but probably not. Move along. The paper is still cited. The question it raised has not gone away. Now, to be clear, this is not a conspiracy. Scientists are not lying to you. The softening is a cultural habit, not a plot. Institutions overpromise certainty because certainty is easier to fund and easier to explain. But the effect on the public is real. People believe the science is more settled than the scientists themselves think it is. And when the softening finally cracks, the number underneath may be one very few people are prepared for. The age of the universe is not a standalone fact. It is an anchor. Almost every other date in cosmology hangs off it. Take the oldest stars. HD 140283, sometimes called the Methuselah star, sits about 200 light-years from Earth. Its measured age has come uncomfortably close to the age of the universe itself. Earlier estimates put it above 14 billion years, older than the universe was supposed to be. Revised calculations pulled it back inside the limit, but only just. A larger universe age would remove that paradox entirely. The star would fit comfortably inside its own cosmos again. Cosmic inflation is another anchor point. The theory that the universe expanded exponentially in the first fraction of its first second depends on very specific timing. A different age changes what inflation had to do, and how fast, and whether it happened the way current models describe. Some cosmologists have already begun proposing alternative frameworks: modified gravity, early dark energy, new particles that decayed before the CMB formed. Each one is an attempt to save the timeline by adding something we cannot see. Each one is a warning sign in its own right. Even the Big Bang itself may need reinterpretation. Not erased, not denied, reinterpreted. Perhaps not a singular event 13.8 billion years ago, but one moment inside a longer, less understood process. The word beginning may be doing more work than the evidence supports. Here is what this actually means for people who have never taken a physics class. Humans are living inside a scientific worldview that is quietly under revision. Not falsified, not overthrown, revised. And that revision is happening at a level the public has not been invited into. Every major shift in cosmology has been preceded by exactly this pattern. Heliocentrism, the expanding universe, the discovery of dark energy itself. In each case, there was a period of tension where old models produced answers that no longer matched new data. The signs are recognizable, and they are here again. So what should the honest answer to how old is the universe actually be? Here is the verdict. The Hubble tension has not closed, it has hardened. Two rigorous measurements of the universe's expansion refuse to agree, and every new instrument confirms the refusal. Webb has produced early universe observations the standard model cannot absorb. Dark energy may be evolving, undermining the constancy the entire framework depends on. Multiple independent lines of evidence now point in the same direction. The universe is older, stranger, or built on different physics than the textbook version claims. The comfortable framing was that science knew how old everything is. The honest framing is that science had a good working number, that number is fraying, and the next number may look very different. Return with me for a moment to those galaxies from the beginning,
The ones Webb caught staring back from an era that was supposed to be empty. They are not surprises. They are not anomalies. They are receipts. Physical evidence sitting in the data that the story humans have been telling about their own cosmic origin was a draft, not a final. A working hypothesis mistaken for a conclusion. This is not a reason to despair. It is not even, really, a reason to be afraid. It is a reason to look at the science more honestly than the press releases have allowed. The willingness of the field to face this tension, even slowly, even reluctantly, is the exact reason a better answer will eventually emerge. That is what real science looks like when it hits the edge of what it knows. The universe is not 13.8 billion years old anymore. It may never have been. And the next number, whatever it turns out to be, will be one that Webb forced humanity to find. Not because anyone wanted to look, because the telescope pointed at the dark, and the dark answered back with something the old models could not accept.